Hello everyone, welcome to the course on operating systems. This is Karthik Gopalan, and in this first lecture I will present to you an introductory overview of operating systems. First, let us look at a simplified view of the various interfaces in a computer system. A computer system can be divided into broadly two components, hardware and software. Hardware consists of things like processor, main memory, and I/O devices, and these three components talk to each other through I/O controllers, memory controller, a system bus, and a memory translation unit. And the way the hardware interacts with the software is through an interface called the instruction set architecture. The instruction set architecture, or ISA, is labeled in this picture through interfaces 8 and 7. Now, everything above the instruction set architecture interface is software. This software includes the operating system itself, as well as user-level processes that do not have the privileges of an operating system, and libraries that are usually linked as part of user-level processes, and they run in user space context. So looking further into the software component, you will see that operating system has many other internal components, and these are not the only components in operating system, but this is just a representative sample of the OS components. So for example, you may have device drivers that form a large part of the operating system, memory management unit, CPU scheduler, file systems, and so forth. So the takeaway from this picture is that in order for the software to interact with the hardware, it has to invoke instructions that are defined as part of the instruction set architecture. The ISA is usually specified by the hardware vendor, or specifically the vendors who make the processors for the system, and the instructions specified in the instruction set architecture are the only ones that the software can invoke to control the hardware. Now, the instruction set architecture itself can be divided into two components. One is the component labeled 8, which is called the system ISA, and the other is the component labeled 7, which is the user ISA. The difference between these two is the level of privilege that comes with each set of instructions. Only the operating system is allowed to execute the instructions that constitute the system ISA, whereas any software in the system, whether user-level processes or operating system, can invoke the instructions that are part of the user ISA. For example, if you have an instruction to manipulate the processor privilege level, then that would be part of system ISA. Similarly, if you have an instruction to issue I/O requests to the I/O devices, say through programmed I/O or direct memory access, then those would be part of the system ISA as well. Likewise, if you have instructions to change the memory permissions or memory privilege level of certain parts of main memory, those instructions may be part of the system ISA as well. On the other hand, user ISA instructions are non-privileged instructions, meaning that these do things that do not require special privileges from the hardware. So for instance, loading and storing to certain allowed parts of the memory would be non-privileged instructions. Executing, say, floating point arithmetic would be non-privileged instruction, and so forth. So with this distinction in mind between user ISA and system ISA, we can look further up the software stack and see how the operating system itself interacts with user-level processes. So user-level processes normally do whatever they're supposed to do. Let's say that you write a program to read a file from the disk, and do some processing on the data that's read from the file. So in order to open, close, read, or write to a file, a user level process cannot do that by itself, so it has to invoke system calls to ask the operating system to execute the I/O operations on its behalf. The system call interface is represented by interface number 3. And once the operating system performs those I/O operations, it can return the results back to the user space process, which can then do user level computation on the data that it has read. So in the simple example, you see the role that system call interface plays in enabling communication between user level processes and operating system. System calls provide a safe interface for user level processes to request services from the underlying operating system. Now we look at again a somewhat informal definition of what is an operating system. Now, operating system can be generally considered to provide many different services, but one of the core reasons why operating system is different from any other software is that it can do things that other ordinary software cannot do. In other words, operating system is considered to be the most privileged software in a computer system. Now, what that means is that OS can do certain special things, like it can issue I/O operations, it can communicate with other computers over the network through network interface, it can control the memory layout, the memory privileges, it can control who can read and write or execute from which parts of main memory, and it can control who runs on the CPU for how long and when. In other words, operating system is responsible for managing all system resources, and it has the privilege to manage all system resources, such as CPU, memory, and I/O devices. Now in this figure, we are seeing an alternative view of the layering of various software components in a system. It's very similar to what we have already learned in the previous slides, except for one additional detail, which is that at the lowest level we see a component called the hypervisor, which is interacting with the operating system through something called a hypercall interface. Now, hypervisor is increasingly taking over the traditional role of operating system as the most privileged software, and the reason being that oftentimes people want to run many different instances of operating systems side by side on the same machine. So in order to arbitrate between different operating systems running at the same time, you need an additional layer of software called the hypervisor, which can be considered as an operating system for operating systems. So this hypervisor is traditionally supposed to be very thin layer with very little overhead, and it provides a machine-like ISA, emulated ISA interface to the operating systems that run on top of it. And in some cases, this hypervisor can communicate with the operating systems it manages through a hypercall interface. What that means is that if operating systems want to request certain special services from the hypervisor, then they can invoke hypercalls into the hypervisor for those special services. Very similar to how processes invoke system calls into the operating system to request special services from the OS. Now comes the question of when does an operating system run? Or in other words, when does it execute? When we power on a computer, the first thing that executes is a piece of firmware called BIOS, or Basic Input-Output System, that it discovers the available hardware, and then it figures out which of the available storage media contains a bootable operating system, and at that point it loads the operating system from the bootable media into the main memory. The operating system has an initialization code called boot code, which executes initializes the available hardware, takes control of the hardware, and then once the initialization process is all done, then the operating system will enter a steady state where at that point it's essentially waiting for certain events to happen to which it can respond. So in the steady state, there are essentially four different ways in which an operating system can execute. The first is when a regular user level process invokes system calls. Now system calls transfer the control of execution from the user level process to some code in the operating system. The system calls execute in the OS, and then the control is handed back to the user level process, much like how regular function calls work within a normal process, except that here system calls are also performing a privileged transition from user space to kernel space, and then back from kernel to user space. The second time then that an operating system can execute is when there are exceptions during the execution of a process. By exceptions, we mean that when a process is executing, let's say it makes an error, for example, dereferencing a null pointer, or divide by zero operation, or accessing invalid memory addresses, and so forth. So in such cases, the processor would raise an exception, which then transfers immediate control to special code inside the operating system that can take care of the exception. Normally, a process may be killed, or the operating system may respond in other ways to an exception depending on the intent of the process. So the third instance when OS code can be invoked is by the hardware. Hardware can generate certain events called interrupts, and these interrupts tell the operating system that a certain event generated by the hardware is ready to be processed. For example, if there's a network card in your system and it receives a packet, then it can send an interrupt through the processor to your OS, and then the operating system would execute a special piece of code that's part of the device driver, and the device driver can then handle the reception of the network packet into the main memory. The fourth way in which an operating system code can be invoked is through kernel threads. Kernel threads are dedicated threads that run with operating system privileges, and they do background maintenance tasks. For example, some threads might log system events of importance that then system administrator should know. Other threads might monitor memory pressure in the system or the amount of memory used, and free up additional memory when the system runs low on free memory. So with the kernel threads, these are constantly running in the background. Sometimes they may sleep, sometimes they may wake up and do certain tasks at periodic intervals, but essentially they are in the kernel context all the time. So system calls, exceptions, interrupts, and kernel threads, these are the primary ways in which operating system code can be invoked. Now we will take a higher level view of the functions of an operating system. The three major tasks of an OS can be categorized as virtualization, concurrency, and persistence. Now we will take a look at each one of these in somewhat more detail. First we start with virtualization. One of the primary jobs of an OS is to make the computer system easier to use for ordinary users, and also easier to program for developers. So what virtualization means is that to take any physical resource in a computer system and make it look like something else, or provide a virtual view of that physical resource. For example, you might have one physical CPU on a computer, and you may have many processes running on that computer. So when all these processes execute, each one of those processes believes that it has a dedicated processor of its own. However, in reality, what's happening is that operating system is virtualizing a single CPU, physical CPU, and make it appear as if each process has a virtual CPU of its own. Likewise, you can extend this analogy to other resources. For example, there is a common pool of physical memory on a computer, and every process that runs gets its own dedicated virtual memory address space, meaning that every process thinks it has its own dedicated memory address space, whereas in reality that virtual memory is being shared on the physical memory with all the other processes running on the computer. And so forth with disks. And on a storage media, you have block-based storage system that have to be accessed through block numbers on the physical disk. However, normal processes may view the storage media as a set of files with a file name, length, attributes, and so forth that they can open, close, read, and write. So this higher level view is of a file provided by a file system is very different from the low level physical view of the hardware media. So, so this is again an example of virtualization of the underlying resources. Next, we look at concurrency as a task performed by the operating system, more specifically managing concurrency. What that means is that as we saw a little while earlier, there are many different events that are constantly happening, and the operating system is responding to those events by executing certain piece of code. So, for example, when there are system calls from user process, there is system call code being executed. When there are exceptions or interrupts, then the corresponding OS code to handle those exceptions and interrupts will be executed. Now, many different tasks can happen independently of each other, and they may even happen at the same time. The operating system's job is to figure out which task or which event to handle first, and how to prioritize the tasks that happen at the same time. So a big complexity in the operating system is due to these concurrent events that need to be processed together. Now, the notion of concurrency also extends into user space processes. For example, a single process may have many different threads, and these threads may each provide a single flow of control within the user space process, and the threads may need to be scheduled by the operating system more or less independently of each other. So concurrency essentially means that the operating system has to juggle the execution of these various tasks. It has to juggle the execution of processes, handling system calls, handling interrupts, exceptions, and so forth. And finally, a major task of the operating system is persistence. What that means is that whenever user level processes generate any data or any output, normally users would want to store the data or save the data. And this data is normally committed to some kind of a persistent storage device, such as hard disks, solid state disks, CD-ROM drives, floppy disks, and so forth. So it's not just enough to save the raw bytes, because raw bytes with themselves don't have any meaning. You also have to attach something called a metadata to this data, which describes the data. For example, if a certain piece of output is a text file, then you have to record somewhere that this is a text file. Or if it's a movie, then you have to record somewhere that this is a movie file, or an audio file, or so forth. So a big part of managing persistence is to organize the data, that is to save both the raw bytes of the data, the contents, and also to manage the metadata associated with the content. A big part of storage systems increasingly is also being able to share data with others over the network or through cloud-based services. And you have to also be able to provide some reliability. For example, if your data is corrupted or it is lost, then you should have some mechanism to recover the data. which means providing some sort of fault tolerance to the underlying storage media. And finally, a key component of any storage system is access control, meaning that you want to prevent unauthorized access to certain data. Only users who are authorized to access a particular piece of data are allowed, and the others are not allowed from accessing the data. Operating systems have had a very rich and interesting history. Now, we'll look at some of this history very briefly. Uh, the earliest operating systems in the 1950s and 60s, they were designed for early mainframes systems, and essentially users were responsible for bringing their own operating systems with their programs. So if you were a programmer and you wrote an application, you had to essentially have libraries that would also know how to manage the underlying hardware. There was not much support for multi-programming and multi-user environment or interactivity. These were very simple batch processing systems. In the 1960s and 70s, people started developing multi-programming, multi-user systems, again for mainframe environments. Here, they started adding features like concurrency, memory management, privilege separation between user space and operating system, and so forth. So some of the earliest operating systems that were pioneering in this field were the Multics system, which was both a combination of hardware and software, but a lot of the early fundamental developments in OS were from the Multics system. Then came the early Unix operating system, which was the first operating system to be written in a high-level language, namely the C language, and this provided many higher-level abstractions such as file systems, interprocess communication, and the C language itself was a first in the Unix operating system. In the 1980s era, people wanted to have personal computers, and then correspondingly, operating systems were designed for personal computing environments. These were much simpler than those for mainframes. These were usually single user based operating systems, and they didn't have much of multitasking and multi-programming or concurrent programming environments. Examples include, of course, Mac OS and DOS, which was an early version of operating system on IBM PCs, followed by Windows in its various variants. 1980s also saw the evolution of Unix into a number of variants in the commercial space. Various companies such as IBM, Apple, HP, Sun, and so forth had their own versions of Unix operating systems. And a lot of intellectual property issues arose where people started claiming various intellectual components in the OS Unix development. Um, then this was followed in the 1990s by the open source movement, and operating systems, Unix variants specifically, such as FreeBSD and Linux, were developed. They were widely accepted. Linux in particular took a foothold because it was freely available through open source license, and anybody could use it or modify it any way they wanted. This became very popular, and Linux has over the years become the predominant operating system in all environments, right from enterprise server environments, cloud-based systems, to desktop systems, and even embedded systems. 1990s also saw the incorporation of concurrency and parallelism, and specifically support for kernel level threads. Beyond 2000, we saw the rise of both mobile devices as personal computing assistants, and also the cloud-based environments to support the computing requirements of these mobile devices. So operating systems have evolved extensively in both of these extremes, where for handheld personal computing devices such as iPhones, iPads, and so on, There are operating systems that specifically cater to users' need in these environments, whereas in cloud-based platform where multi-tenancy is required, there has been a rise of support for virtualization features such as virtual machines and containers, and the necessary infrastructure to support these on a very large scale. So operating systems such as Android and iOS on handheld devices are very popular, whereas in the cloud environment, essentially a new class of operating systems called hypervisors are have taken a foothold, and among these there are platforms such as VMware's ESX server, Zen hypervisor, and Linux itself has comes bundled with a hypervisor called the KVM. So the rest of this lecture basically deals with class logistics, and I won't be going over these in this recorded lecture, but you please feel free to browse the remaining slides, and again feel free to also ask me any questions you may have about these class logistics.